Today we're going to discuss colligative properties. The colligative properties we're going to be dealing with are vapor pressure lowering, boiling point elevation, and freezing point depression. So in your note packet, we want to fill in when you dissolve a non-volatile solute, that's something that doesn't evaporate easily, into water, the freezing point and boiling point of water change. So for example, if you dissolve salt in water, it's going to have a different boiling point than pure water alone. So physical properties of any solution, meaning something like salt dissolved in water, a solution, homogeneous mixture, differ from pure water alone. And that's because the presence of the solute particles, the salt particles in that example, are going to affect the boiling point. Those physical properties are what we call colligative properties. Colligative properties are dependent on the number of ions in solution and the size of the particles. So what that means is if you have larger solute particles, the freezing point will be depressed, but not as much as if the particles were smaller. And the boiling point will still be elevated, but not as much as if the particles are smaller. So the smaller the solute particle, the more the freezing point is going to be lowered, and the more the boiling point is going to be elevated. So the three colligative properties we're looking at today are vapor pressure lowering, meaning that when you add a solute to water, the vapor pressure will go down. When you add a solute to water, the boiling point will go up, like adding salt to water makes a higher boiling point. And freezing point depression or lowering, meaning if you add a salt or any solute to water, the freezing point goes down. So let's first look at vapor pressure. Remember, when you increase the temperature of a liquid, the molecules are going to start to move faster, and as they're moving faster, some of them are going to escape from the liquid form and enter the vapor phase. We've already talked about this is known as evaporation or vaporization. The pressure that the vapor exerts in the gas phase is known as the vapor pressure. This picture is just showing you two different flasks, one at a lower temperature on the left and one at a higher temperature on the right. We use this word equilibrium on the right to describe when you have molecules are entering the vapor phase. So as liquid gets heated up, they start to become a vapor, but since this is capped, some of the gas will then condense back and become a liquid. So we have this equilibrium where the amount of liquid will stay the same with the cap on it. Some will be evaporating and some will be condensing at the same rate. So a liquid will boil when the vapor pressure increases and the vapor pressure is equal to the atmospheric pressure. This is why in areas like Denver, Colorado, when there's a higher altitude, meaning that there's less pressure pushing down, less atmospheric pressure, the boiling point is going to be lower. So things like cooking pasta, you can cook at a lower temperature. When we talk about vapor pressure, often the word volatile and non-volatile come up. I just want to remind you that a liquid is volatile if it evaporates easily. That would mean it has a really high vapor pressure. It's going to enter the vapor pressure very easily. So acetone, something that you may be familiar with, like nail polish remover, has a high vapor pressure. If a liquid vaporizes easily, the intermolecular forces are weak. Remember, we said gases have weak intermolecular forces. So if something is entering the gas phase relatively easily, meaning highly volatile, it has weak intermolecular forces. On the other hand, if a liquid is non-volatile, meaning it doesn't evaporate easily, for example, greasy, oily substances do not vaporize easily. They have stronger intermolecular forces keeping the molecules together. So non-volatile solutes, those that don't evaporate easily, have a low vapor pressure. There's not a lot of pressure being exerted, trying to force it into the gas phase. The ions are surrounded by water molecules, and the number of solvent molecules that have enough energy to escape to the vapor is low. So if a liquid has a low vapor pressure, it's going to have a very high boiling point. So if you open up your reference table, we have a chart that looks at vapor pressure and temperature, as you see on table H. So take a minute to pause the video at this point and go open up the table H. You'll see that there is a dashed line here, 101.3 kPa's. Where a line crosses that dashed line is the boiling point. So this is the atmospheric pressure. Where the vapor pressure meets the atmospheric pressure is the boiling point. So let's go over and look at, there are four different substances here, propanone, ethanol, water, and ethanoic acid. Let's look at water. Where water, vapor pressure line, crosses the atmospheric pressure line is 100 degrees Celsius, which makes sense because we know that water boils at 100 degrees Celsius. Some other things to notice is that as you look at increasing temperature, increases vapor pressure. Ethanoic acid has the highest boiling point if you look over here. And as we said, if you were to look at any temperature, let's say 75 degrees Celsius, ethanoic acid would have the lowest vapor point of any of these four liquids at any temperature. So 75 degrees Celsius, ethanoic acid has the lowest vapor pressure, then water, then ethanol, then propanone. So ethanoic acid has the lowest vapor pressure at any temperature and has the highest boiling point. We also have discussed this relationship of boiling point intermolecular forces. So ethanoic acid has the highest boiling point and would have the strongest intermolecular forces. So that's an idea that we've seen over and over now. Higher boiling point, stronger intermolecular forces. Now we could add that if you're going to have strong intermolecular forces and a high boiling point, it's going to correspond to a lower vapor pressure at any temperature. The next question in your notes asks for a reference table H learning check. What is the vapor pressure of water at 105 degrees Celsius? So you go to 105 degrees Celsius, and you want to be careful noticing the axes here. We're going up by 5 over here, and we're going up by 10 here, so just be careful. So they say 105 degrees Celsius, so we go to 105 degrees Celsius, you go up till you hit the water line, and then you're going to go over and read the temperature, and you end up with about 120 kilopascals. So where the water line meets that line, come over, and 120 kPa. So in your notes you could write 120 kPas. The next question asks about, as water in a steel container is cooled from 20 to 10 degrees Celsius, its vapor pressure increases, decreases, or remains the same. So let's find the water line. Here's water. As it's cooled from 20 to 10 degrees Celsius, so what's happening? Is it going up, down, or remaining the same? I would say that we are going down. So you could fill in decreases in your notes. Vapor pressure of ethanol at 85 degrees Celsius. So we're going to go to 85 degrees Celsius, go up till we hit the ethanol line, and then you would go over, and I would probably say around 122 kPas. And the last question in your notes, what is the temperature of propanone if the vapor pressure is 160 kPas? So we'll go to 160 kPas, go over till we hit the propanone line, and we'll go down and read the temperature, and I would probably say around 71 degrees Celsius. So we've already mentioned that when you add a solute to water, the boiling point goes up. There is a difference in the temperature between boiling point of a solution, example salt and water, and that of just the pure solvent water. Whenever you add a solute to a liquid, the boiling point will go up. It takes now additional kinetic energy for the solvent to overcome the attractive forces, keeping them together as a liquid and making the substance boil. One thing to keep in mind is that the more moles, or the more concentration of solute particles dissolved in the solvent, the higher the boiling point will be. So the greater the effect will be. Also, ionic particles, since they're going to break up into ions, are going to have a greater effect than covalent substances. So for example, salt will raise the boiling point of water more than something like sugar would be, which is covalent. So we have 1 mole of sugar dissolved in water, or we could have 1 mole of an ionic substance like salt dissolved in water, and the salt will break up into sodium and chloride ions, so 2 ions, greater concentration of ions, compared to the sugar, which just stays as 1 piece. The ionic substance will have more of an effect, raise the boiling point more. So we could take 2 ionic substances like calcium chloride and potassium chloride, dissolve them in water. The calcium chloride will break up into 3 ions, 1 calcium and 2 chloride, so it's going to have a greater effect than something like potassium chloride, which would only break up into 2 ions. So the greater the ions, the greater the effect will be. You could also change the molarity of different solutions. So if we look here, we have a 1 molar solution of potassium nitrate, a 1 molar solution of calcium nitrate, and a 2 molar solution of calcium nitrate. The 2 molar solution will produce more moles of ions, because molarity is moles over liters. Since it has more moles of ions, it's going to have a greater effect. Lastly, the freezing point depression is the difference between the regular freezing point of a substance and that when you add salt or any solute to it. When you add a solute like salt to a liquid, the particles of the solid have a certain pattern. The presence of the solute particles are going to disrupt this formation or pattern, and more energy will be withdrawn from a solution than from the pure solvent in order for it to solidify. So the freezing point will go down or lower. This is why you add antifreeze to your car, because it lowers the freezing point of the solution, making it harder for the car radiator to freeze at 0 degrees Celsius. And the same reason we add salt to roads. When you add salt to the road, it lowers the freezing point of the snow. So if it takes 0 to freeze it, it's going to be even lower. So it'll become harder for the snow to turn into ice.